The Routh Stability Criterion is a rigorous means by which a process control engineer can derive the largest possible gain for a controller that we're implementing. And why is this important? Well, when we are tuning our controllers that we're designing for a process, we want to know the limits of the stability that we can go to. And so in that regard, the higher we make our controller gain, the more aggressively our controller will respond to a step change in an input or a disturbance, for example. And we want to determine how aggressive we can make our controller before our system begins to behave unboundedly, when it becomes so aggressive that it's no longer useful and we need to start tuning things down a bit. And so what I'll do in this video is go over an example problem, and that will introduce the concepts behind it, such as the Routh array. And to start off with, let's consider the process transfer function GP, which is equal to 1 over 6s cubed plus 11s squared plus 6s plus 1. And so this is another thing to note about the Routh Stability Criterion, is that this is a pretty high degree polynomial in our denominator of our process control function. And so when we want to determine what the stability of our system is by analyzing the poles of our characteristic equation, it's pretty easy for first and second order polynomials, but once we get into third, fourth, fifth degree polynomials, it gets very tedious, and rigorously evaluating all this stuff is not necessary if we implement the Routh Stability Criterion. And so in this example also, we will consider a simple P-only controller. So the input to our process will simply be Kc, which is directly proportional to the error that is present in our system. And so if we were to look at the control loop of this process, we would have the error coming in, being analyzed by our controller GC, being input to our process GP, and then exiting before being fed back into our controller. And so looking at this system, this closed loop transfer function will have an overall form of GC GP over 1 plus GC GP. And so now if we analyze this denominator, because that's the part we're interested in for determining stability, what we'll find is that our denominator in this equation will be equivalent to 6s cubed plus 11s squared plus 6s plus 1 plus kc. And commonly we'll put these parentheses here. This we set to 0, and we can now look at the first condition of the Routh Stability Criterion, which is the necessary condition. And the necessary condition simply tells us that we need to make sure that every coefficient in front of all of these terms is positive. So 6 is a positive number, 11, 6, and 1 plus kc. So the first thing we'll recognize is that 1 plus kc must be greater than 0. We've already derived the necessary condition. Kc must be greater than minus 1. And so we already have half the battle done, but there's a lot more work to be done. So the next thing to do is look at the sufficient condition. And the sufficient condition involves the Routh array. And the Routh array looks like this. And so if we were to start labeling our coefficients here, A3, A2, A1, A0, we can begin to better understand what is going on here in our Routh array. And so if you look it up in a textbook, the Routh array has this form. So we'll have row 1, 2, 3, and we continue onwards to row n plus 1, which in this case, because our degree is 3, it would be 4. And then what we would have here is an minus 2, an minus 4, and so on. And so to make this a generic Routh array, I'll keep it in this form. So we'd have dot 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 out to n plus 1 for the number of rows that we have. Row 2 would be equivalent to an minus 1, an minus 3, an minus 5, and so on. And then finally in row 3, what we have are coefficients b1, b2, b3 onwards, c1, c2, c3 onwards in row 4. And so the next thing to do is ask ourselves, what is this term b1 and b2? So b1 is equivalent to a sub n minus 1 times a sub n minus 2, quantity minus a sub n times a sub n minus 3. And we're going to divide this term by a sub n minus 1. And when you see the pattern here, it can get easy to start waving your hand, but it is critical that you don't do it at this point, because I would really like to point out these three terms, they do not change. So in our term b2 is still equivalent to a sub n minus 1. Now we have a sub n minus 4, and then minus a sub n times a sub n minus 5. And then we divide this term by, again, a sub n minus 1. So the key takeaway here is that as we move across our rows, past past row 2, these three terms do not change. And that was something that I missed when I first learned this stuff, so hopefully you guys don't. And so the same can be said of these coefficients C1 and onwards. And so to begin plugging in the numbers that we have from our example here, I'll rewrite it. We have 6s cubed plus 11s squared plus 6s plus 1 plus kc must equal 0. We're going to look at this equation. We're going to recognize that, a3 is equal to 6, a2 must be equal to 11, a1 is equal to 6, and a naught is equal to 1 plus kc. And so to also spell this out a little bit more explicitly, we now have a sub n minus 1, a sub n minus 2, a sub n minus 3. And so now we can begin to plug these in and generate our Routh array, like so. So if we take this stuff, plug it in, we'll have row 1, 2, 3, and 4. And we will have a sub n, which was equivalent to 6, a sub n minus 2, which was also equivalent to 6, a sub n minus 4 is equal to 0 because it doesn't exist, and we can continue to pad our Routh array with zeros, like so, if you want. And moving on to row 2, a sub n minus 1 was 11, and a sub n minus 3 was equal to 1 plus kc, our controller gain. And the same can be said of a sub n minus 5 and a sub n minus 7. So now we get down to our terms b1, b2, and so forth. What we're going to do for our term b1 is plug and chug. So b1 will be equal to, we'll have 6 times 11 minus 6 times 1 plus kc, quantity divided by 11. And we can simplify this down to 6 over 11 times the quantity 11 minus 1, which is 10, so 10 minus kc. And a side note here, you really should see a minus sign here, because doing this rigorous Routh array involves a lot of algebra. This minus sign is implying that we're going to be deriving some kind of maximum kc value, which is what we want to do, because all the necessary condition gave us was a minimum kc value, which we don't really care about. We care about what's the point at which our system begins to become unstable. And so this is a good sanity check while you're doing a Routh array. If you don't have a minus sign here, it means you made a mistake. You got to go back and check. And so if we continue to evaluate this, what we'd find is that b2 is equal to 0. And now that we have derived that, You can plug in this form here, plug in the values that we just determined. So we would have 6/11 times 10 minus kc for B1 and 0 for B2. And then finally, an interesting characteristic with the Routh array is that our final term in the n+1 row, or the first in column 1 of n+1 row in the Routh array, we will have A naught. And A naught, as we'll recall in this case, was simply 1 plus kc. And so we don't really need to rigorously evaluate, but it's just a nice little thing to know. And so another thing it tells us, and if you rigorously evaluate it, is you will find that you will get your necessary condition. And so it is another sanity check you perform along the way to see if you made any algebra mistakes. And so the gist, or the holy grail here, is this column 1 of our Routh array. And so what our Routh array is telling us is that every single element in the first column must be positive. And if it is not the case, then our transfer function is, our overall transfer function is not stable. But in this case, or what we're doing is we're evaluating the condition. So in this case, what we know, we already knew this right here from our necessary condition, but now we learn this, our sufficient condition. The sufficient condition tells us that 6/11 times 10 minus kc must be positive. And so if we multiply both sides by 11/6, this cancels, and we will recognize that 10 must be greater than kc. And so this is the key takeaway, because now we have determined that -1 must be less than kc, must be less than 10. And so this is the range of kc values, and 10 specifically is the upper limit of our controller gain before we realize instability, before our controller becomes so aggressive that it is no longer making our system stable. And so this concludes the Routh array and how we're able to use it to determine the stability of a given transfer function and evaluate our tuning parameters, the range that we have with our tuning parameters. I hope you guys find it useful. Let me know if you have any questions, and thanks for watching.